I'm Abhishek Suwalka and this is my course project explanation video in VLSI course. So my topic is applying machine learning in VLSI. Base paper I have chosen is this one. A timing engine inspired graph neural network model for pre-routing slack prediction. You must be thinking what is pre-routing, what is slack, what is like why do we have to predict it? So before going through the video, I have given a few words which will help you to understand the base paper or my report. So this is the dictionary which I have made for this particular paper. Here I have given like complete explanation of what a particular word means in this paper. Let us come to the paper and why do we have to predict it? So every time we want to decrease the slack, the time taken by a signal from one interconnect to other interconnect, we have to decrease it. And we also have to decrease the crosstalk. So we cannot build circuits and test on them. Okay, this one is giving less error, this one is giving more error. So what do? Is we build models and then we predict, okay, this circuit will give better results or this circuit will be better because this model prediction is economically better and less time consuming. So that is what is explained in here. And then what this paper suggests is they suggest a graph neural network model, but actually there are a lot of graph neural network models in EDA, electronic design automation, but they have given a better way to make the model or adjustment in previous models, because the problem with graph neural network models is after 3 or 4 or 5 layers, because of over smoothing, they do not give good results. Like how many layers are there, that is very important in graph neural network. After 3 or 4 layers, the next layers are useless. This is the introduction part, and here they have given what is the state of the art model, what is the problem in it, because it is a half perimeter wavelength model, so it has some problems. What they have done is they use this random forest model to check the performance of their own model, to compare their performance with this model. So I have implemented this random forest model also and their model also. So this is the problem with graph neural network, basic vanilla graph neural network. If you train on basic graph neural network, this is the problem. The problem is over smoothing. Let us see what is the difference between vanilla graph neural network and the implemented or the proposed model. So this is the equation of basic graph neural network, where they calculate this H hinge loss, and here this is the GCNII, which is the proposed model. This has this modified equation which has residual connection and identity mapping. Residual connection, what it does is it forwards the feedback from previous layers so that the information is retained in the model. In graph neural network, the information is not retained after a few iterations. Like once you go for level 3 or layer 4, then the information from layer 1 or layer 2 is lost. So this is what this part actually does. It kind of gives the information again and again to the model, so it can predict on basis of that also. This will also be an input in predicting the output. This is my report and I have explained why do we need this model, and these are the challenges faced. This is very important because I was working for the first time on GNN, so my environmental setup, it was quite hard. I will tell you in the code what libraries you have to install that will be best for the environment setup. And then training a neural network is very computationally expensive. You have to give a lot of time and a lot of computer resources, so such that the trained model will become good. Like sometimes you have to go to 10,000 iterations or epoch or sometimes you have to go for 1 lakh iterations or epoch. So the model takes time to train, but it gives good results once it is trained, so it is reusable. It is like one time investment, and the training time is a bit of challenge. This is the proposed model in the paper which I am implementing. I have also implemented this random forest. I have also implemented the code for GCNII, and this is the net embedding model. This diagram represent the delay propagation model which we are implementing in the model. Let us come to data. This is our data. These 21 files are different circuits taken from an open source software. These are number of nodes, these are not net edges and cells, and these are total endpoints of a graph. Before explaining the accuracy in random forest, let us go for code. So here I was checking if the GPU is working fine. Here I have imported the files. Torch, PyTorch is important, DGL library it is important, and other libraries they are important. What I have done is, this is all the files. The files are here in data folder in netstat. These are 21 files. This is our data. So here I have transformed data basically, and this is data preparation state. What I have done is I have combined all the data in this data train and data test, so you don't have to do it again and again. I have saved this data in this file, data train data test .pt. This is a combined file of all data, and then here I have loaded this data. Here in this step I am loading this data which I have created in this module. In this module what I have done is, I have done the same things, importing libraries, and then here I have imported the data. This is what data looks like number of edges, number of nodes, and number of endpoints. This is the data, this is the dictionary. So let us discuss about the random forest implementation. This is the code I have written for training the random forest, and here I save the random forest model, and this is the accuracy given by random forest model. On this is the training data, and on training data it is giving good accuracy, very good accuracy, and on test data also it is giving good accuracy except a few of the circuits. And next thing, I have tried leave one out technique, where the model is trained on all data except one circuit, and then we test it on that circuit. So the model have never seen the test subject, but then we test it on that subject. To generalize the model, we have done this technique, and when we did not choose this one and trained on rest of the data, it is giving 96% accuracy or R2 score in this. And this is the performance of different circuits in leave one out. Here I have done the GNN part. Here I have imported the libraries as it is. I have imported other libraries which are required. This is the T file which contains the classes. It gives output and input streams. I have commented what the code is about, so I need not to explain it all, but yeah, this is where I import the data which I have created in first step. This is what the data looks like. This is the model, the MLP or deep GNN model, and this is net convolution class. This is the signal prop class. So this is the complete implementation of the model, and this is the code for model. I have not trained it yet, in this step, but then in this step I train the model, and then I save the model in this directory. So this is the code for testing the model, and this is the code for training. Like, this is the code for training. Here I run the code for training the model and then testing it. So at epoch 0 the net delay was 2.33, and the R2 score was almost negative for everything, which means it is giving very bad performance. Then as we go forward, the net delay starts decreasing. As you can see, the net delay is decreasing and the model is getting better. At epoch 400, or the 400th iteration, a few circuits are giving negative R2 score scale. So what I've done is, let's check at 5000 epoch. This is 5000 epoch. Here net delay is 0.06 and the R2 score is like increasing, still negative for a few circuits. It is not giving good performance on a few circuits. So let's check on 10,000th epoch or iteration. This is circuit at 10,000th epoch. So net delay is 0.05 and it is giving 90% R2 score, and almost everything is 90%, and it has not checked on test data, but test data is also giving good score now at epoch 10,180. And what I have done is I have saved all these models so that we do not have to train it again and again in checkpoints and train GNN, because this is GNN. So for every 200th iteration I have saved the model. I have saved it till here. So this is the implementation of deep GNN or GCNII, which is the model implemented in the paper. And this class is useful because we have to stream or write text on the screen so that we know what's happening in the model. And this is where I create homographs or homobigraphs using the data. And this is where I import the data. Here I'm importing it, and this is the MLP class and all the classes which will be useful in this code. This is the code where I test the model. I am not running this code, I have just created a function. I will call the function and run it later. This is code to train the model. This is where the model is saved. We have 15 n layers. When we increase these n layers, it will increase our computational complexity or even the batch size. If we select higher batch size, it will cost us more. And here I have chosen 10,000 epochs, but I had to stop it for 5,000 epochs only. Initially the training loss was 208 and finally it has gone to 5. So as you can see, at 133 iteration the training loss is 40, then it is decreasing. And I have saved all the models in .pth or .pt. Data is in .pt files and model is in .pth files. As you can see here, this is our model for deep GNN. So that was it. Now let us come to the score or the accuracy. This is the R2 score for random forest model, and this is for test data random forest. This is the code. This is the score for leave one out evaluation. And initially when I started this GCN model, in initial steps it was varying a lot, and test data also was varying a lot. Now at epoch 14,459 the R2 score has improved a lot. This is the table for GCNII model, or the model which is proposed in the paper. Thank you.